It's your turn.
Okay.
Bye.
So, okay. Thank you very much. Good afternoon, everyone. So first, I would like to thank Stefania and all the staff of GGI for organizing this fantastic day that we can talk about our research that has been conducted last year, or this year, in fact. Yeah, so today I'm going to talk about some of my recent work on integrable quantum circuits from statistical mechanics. I apologize for this weird font. It's probably because when I converted into PDF, they distort a little bit the thing, but it doesn't matter. So it's based on some of my recent work with my collaborator in Amsterdam in this paper, and also some work with my collaborator in Paris that's still preparing. And before I start to tell you about what is, integrable quantum circuits, I would like to just motivate you why we're interested in these kind of problems. So in fact, I'm really interested in out of equilibrium physics in quantum mechanical systems. And one important thing is that out of equilibrium phenomena are really ubiquitous. So it's really everywhere. If you're interested in cosmology, you look at the sky, or the universe is evolving. It's not in an equilibrium. Or if you're interested in drinking your coffee, well, if you wait long enough, get cold. So almost everything around us, they are out of equilibrium intrinsically. And more importantly, for quantum mechanical systems, there are some recent experiments that really reveal very interesting phenomena, such as this one shown here is called a quantum Newton's cradle, where you prepare two blobs of Bose gases, so in a one-dimensional potential, where you just release them because of the confining potential, say hyperbolic. They start to move, and then they move up, and then they come down again. So normally, if you imagine there are strong interaction between them, these two blobs of gases, then obviously you would expect that these two system will get thermalized very soon. So they will become just like something homogeneous, maybe something like that. However, if you do these experiments, you just sort of take pictures of these Bose gases, you see that they undergo almost thousands of collisions without being really thermalized. And this is kind of strange because that's not what we expect from a generic chaotic system. But turns out that it's precisely because the interaction is very close to a so-called integrable system, it prevented from thermalizing, and you can observe all this kind of interesting Newton's cradle-like physics. And more specifically today, because this is still experiments with, let's say, continuous time evolution, but more recently, there are also like many important experiments on basically discrete space-time like dynamics. So they can be performed on a quantum computer or some quantum chips where this kind of the interaction is done by some so-called quantum gates. Especially there's a very remarkable experiments done by Google and other teams where they can really simulate quantum systems with discrete space-time evolution. And another motivation for me is that I'm very interested in exactly solvable models. So they exist in many guises. For example, in statistical mechanics, you can study the so-called 6-vertex model with certain boundary condition, and you can observe some very interesting phenomena, such as there's some frozen and fluctuating region. And what's really remarkable is that this model can be solved exactly such that you can, for example, study what is the fluctuation or what is the shape of these fluctuating parts in a closed form formula, which is very impressive. And in a more quantum mechanical perspective, well, you can study some so-called quantum spin chains where there are some excitations called spin-ons. So they can be described exactly as some kind of kinks in these quantum mechanical systems, where you can get a very good match between the real experiments and theoretical calculations. So they're actually very nice because, yeah. So what I aim to tell you today maybe is just to show you that you can really solve some even discrete space-time quantum mechanical systems analytically using this kind of method. So first of all, today I want to tell you what is exactly why it is a quantum circuit. So it's related to so-called Fouquet systems in quantum mechanics, and then I'll show you the the main toolkit that I use is called Yang-Baxter integrability. In the end, even though it's a quite technical thing, but yeah, you can understand everything in terms of pictures. And then the main result today is to show you the generic way of constructing quantum circuits that are integrable, so which I call it, well, Fouquet-Baxterization, and some conclusion and outlook. So usually when we consider dynamics of quantum mechanical systems, we think of time-independent Hamiltonian. However, now today I would like to consider a time-dependent one. So Hamiltonian is not really, so energy is not conserved now because I break the time translation invariance. And the Hamiltonian, however, is periodic in this capital T. So if you wait long enough for integer values of this capital T, the Hamiltonian becomes back to itself. So suppose that this Hamiltonian, they don't commute while this kind of time evolution, then the strobostropically speaking, the time evolution operator can be written in terms of a path ordered exponential of this integral of this Hamiltonian. However, let's again simplify the model a bit further. So we consider some let's say sort of quantum Hamiltonian that is written in terms of nearest neighbor interactions. So it's on the lattice and it only interacts with the nearest neighbor. And then we can write this sum into two terms. First is the odd sum over, kind of start with the odd terms, and the other with even terms. So you can see that since they acting on different spins or quantum mechanicals, what fermions or something like this, so they commute among all these H1 as well as H2. So the real Hamiltonian that I want to consider is kind of a model that for between time from 0 to t it's H1, and from t to 2t is H2. So now, okay, the period is 2t now. And in that case, well, the time evolution operator for a fixed, let's say, okay, period, strobostropically, so for each period, can be written, so this exponential can be written in terms of the product of two terms. So first is exponential of H1, the other exponential of H2. And since this model is only involved with nearest neighbor terms, so we can write this exponential in terms of product of all the local exponential of the local terms. So this, I would call this, maybe this is the A here, and the B is on the second layer. So basically what I showed you is that by using this Fouquet time-dependent Hamiltonian, well, if we're only interested in the time evolution of the integer of the period, then we can write basically the time evolution in terms of these individual quantum gates that only acting on the nearest neighbor. Yeah, so this is like a way that, since we have the quantum circuits from these quantum computers, we can use this to simulate this seemingly complicated Hamiltonian. And one question that one may ask is that if we start with this H, which H1 plus H2 is sort of a quantum integrable system, what happened with this time evolution operator? But before that, I want to tell you what is integrability. So in a very simple term, which maybe many of you are particle physicists, you can think of it as the S matrix of the model is factorizable. So when you imagine that you have 3 particles of incoming particles, and you also have 3 particles that outgoing. So a Yang-Baxter relation tells us that all 3 body scattering can be factorized into 2 body scattering. So in another diagram, you can think of it, maybe if you scatter between 1 and 2 first, and then 1, 3, and then 2 and 3, is the same as when you scatter 2 and 3 first, and then 1, 3, and 1, 2. Okay, so in the more like kind of condensed matter physics terms, these are maybe not elementary particles, but maybe they are the excitations of the system, which is called quasi-particles. Okay, in the more mathematical terms, we are thinking about some Hilbert space that kind of can be tensorized as from 1 to L side of some local, let's say, finite dimensional Hilbert space. So you can think of this as quantum spins or qubits or qubits. So I can define some operator called the R matrix, which acting on 2 of these quantum spins in such way that it depends on 2 spectral parameters. So this you can think of in terms of particles. They are just the rapidities or the momentum of the particles, and you can write basically the Yang-Baxter relation in this way. And this is probably more direct related to the vertex model in statistical mechanics that you construct. So one of the remarkable consequences of Yang-Baxter relation is that you can construct this operator called the monodromy matrix, which is a product of all these R matrices that share the same auxiliary space, and this M is like, you can think of it as physical space. So by using the Yang-Baxter relation, you can prove that you act on the R matrix on the left, and then you can move all the R matrix through like a train, well, to the right, and you can interchange basically these 2 monodromy matrices. And furthermore, if you trace over this auxiliary space, so now you only have operator acting on all these physical spaces, you get the so-called transfer matrices, and they commute because of the Yang-Baxter relation. And another important ingredient is that I also put some parameter called psi. So this U, they are associated with this horizontal line, if you want. And these psi's, they are associated with this vertical line. So you can think of, yeah, something like this, where I need to put different, so these psi's, they are called inhomogeneities. I need to use different inhomogeneities to construct the quantum circuits. And it's very obvious that if you have these transfer matrices that they are in evolution, you can expand over this spectral parameter, because it commutes for any U and V, so that you can construct the conserved quantities by expanding over the logarithm of these transfer matrices. And turns out that you can do it for, in principle, for infinite many order. And in some cases, they become the conservation laws that in terms of local densities. So the Hamiltonian, if you want, that showed as a big H is sort of the expansion over the for n equals 2 here. And another ingredient that I need for the circuits is that I need to define the permutation operator, which acting also on the 2 quantum spins. And what it does is that when you push through this permutation operator, you basically change the operator acting on side A to side B. Okay, so the main result of the day, well, it's a theorem that if you choose the homogeneity in such a way that for all the odd side to be 0 and even side to be some alpha, can be any complex number, and you have a system size which is even number. So where I define this operator called R check, which is the R matrices multiplied by the permutation operator. And what the theorem says, if you consider this evolution operator as product of 2 layers of this R check, so basically depicted here, and this depends on only one parameter called alpha here. So this evolution operator commute with the transfer matrix for any U. So if this operator commute with the transfer matrix, what it means is that it also commutes with the infinite many conservation laws that you can do by that I showed on the previous slides. And this means that, okay, also this time evolution operator also commutes with infinite many conservation laws, and hence it's integrable. So I will not show you how algebraically how to prove this statement, which is not very difficult. But instead, I just want to show you some kind of a graphic way of understanding what is going on. So I showed you that this transfer matrix, which is usually how you draw, is like in this way. So it's on a square lattice in this way. And when you choose the spectral parameter to be 0, so for all the odd side, in this specific case, it becomes permutation operator, which you can, permutation is just, you can write the operator in terms of this way of drawing it. So you just have 2 copies of them. And then you also need some operator which shift the circuits to the right by 2 sides, which is not very important. Anyway, so you can just draw this like that. And now you just do a simple exercise of, straighten these lines. So they are wiggly now, but if you, stretch them, and what you will find is some model that looks like this. This is nothing but just the product of this R-check operator that I showed you before. So this is the time evolution operator. And the reason why you can sort of understand why we need this kind of R-check here is because so the R is kind of defined on these square lattices, and now I'm kind of switching. I need to acting further on this permutation operator to kind of switch the indices on this tensor. So that's why it's like 45 degrees. So it's tilted lattice. So basically what it says is that the time evolution operator is nothing but 2 copies of transform matrices, sort of. And this really proves the integrability. Okay, so hopefully I still have a bit of time. So I'll just show you one example. So one notable example is called 6-vertex model. And it's acting on the Hilbert space of, let's say, spin 1/2. So they are like basically 2-dimensional Hilbert space. So these are R matrix, they acting on a 4x4. It is a 4x4 matrix, and it happens to be that this R-check is just exponential of some h, where this h is nothing but the spin 1/2 xxz Hamiltonian. Okay, explicitly it's written here, but you don't need to worry about that. So the interesting fact is that now this model, it depends on this parameter eta, which is called defines the so-called anisotropy delta here. It's a fixed parameter that you give to start your construction, and this eta can in principle be purely imaginary, and in that case this delta is smaller than 1. So the absolute value delta is smaller than 1. However, in this case, this parameter, so sinh eta, it is imaginary. So basically your Hamiltonian here, you put in your exponential of this Hamiltonian here, has some imaginary magnetic field. So which means that now your quantum gate here is not unitary. So in principle, this is a problem, because usually we want to study a unitary quantum mechanics. So however, what's kind of, okay, it might sound discouraging that it's non-unitary, but let's take a look at the spectrum of the time evolution operator. It turns out that the time evolution operator, even though it consists of non-unitary quantum gates, it can still be pseudo-unitary. Namely, there's kind of a phase diagram depending on the value of eta here. And you see that if you numerically calculating the spectrum of this time evolution operator UF here, you see that in the regime 1, they still locates at the unit circle, which means that you can do some similarity transformation to make it unitary again. And on this regime 2, you see that it becomes kind of more generically not, the modular is not 1 anymore, and this hints that what's happening here is that there's a kind of anti-unitary symmetry breaking that's very similar to the famous PT symmetric quantum mechanics, where they also have similar phenomena. And another remarkable thing is that this happens not only at a thermodynamic limit, namely infinite many spins. Actually, it happens already for a finite number of spins, like 6 or 8 spins. You can already observe this phenomena, and the transition will not change. And there's also a very specific, interesting point, which is at this gamma equals pi over 2. And in this case, the model becomes free fermionic. And actually, if you study the model here, you will find out that this is related to some non-compact conformal field theory, which people are interested in. Okay, but okay. Without further ado, I just conclude what I discussed today. So I showed you a generic way of constructing integrable circuits. So which is this UF that I showed you. So it's in terms of this quantum circuits that. So this works for any solution to Yang-Baxter equation. So this R, if you find any R that satisfies Yang-Baxter relation, you can use it to construct the quantum circuits that's integrable. And also showed you some some result that there's a bit of anti-unitary symmetry breaking in 6 vertex circuits, which people hasn't studied quite much before. And actually, in our paper, we showed many other things, which I didn't have time to discuss. For example, I showed you the one that's kind of periodic boundary condition. Actually, you can make it also open. This relates to so-called boundary Yang-Baxter relation. And also, you can study the disorder case, which is in some unpublished notes that I have. And also, you can generalize your circuits not only to just nearest neighbor quantum gates, but you can make it to like n qubit or qubit quantum gates that may be similar to this one. It can also be integrable, which is related to putting the homogeneity with different periodicity. And there's some other way of constructing integrable circuits, which I discovered much later. In that case, we are not using basically Yang-Baxter relation, but to use star triangle relation. And this is kind of a way of just to demonstrate how it's kind of there's a very acute relation between star triangle and Yang-Baxter, which can be shown in this. So this is equivalently also a Yang-Baxter relation. Yeah, but this will be in the upcoming publication. Okay, thank you very much for your attention.